Then he will talk about approximation theory of structured deep neural networks.
Thank you very much. Yeah, it's my great honor to speak at this workshop. First, I want to thank the organizers, Professor Ming, Professor Mazumi, and Professor Sugiyama. This is a famous center, although I've never been here, but I know that you have many well-known researchers in AI and machine learning. Today, I want to describe a mathematical theory of structured deep neural networks. So this is the outline. I want to describe a little bit about structured deep neural networks, and then review the classical theory of fully connected neural networks, and then turn to ReLU networks, and then mathematical theory of deep CNNs. So since we all know powerful applications of deep learning in speech recognition, image, computer vision, and natural language processing. So I don't have to say this again, but let me mention that most of the time to deal with big data, neural networks often have structures. So the first family of deep neural networks used in practice, I will describe a little bit, is convolutional neural networks induced by convolutions. It has been applied in speech recognition, computer vision, and some other areas. Then recurrent neural networks, GANs, and these days transformers and some others. So let me just mention one example, that is the AlexNet. So the input of this AlexNet is a 224 by 224 by 3 image, which is a color image. So if you look at each pixel as one variable, then the dimension of the input data is about 150,000, which is large. So if you want to use fully connected neural networks to process this data, usually the number of neurons is larger than the dimension. Then the number of parameters you need to train is a lot. So the idea of deep CNN here in AlexNet is to reduce the dimension first from about 150,000 to about 2,000. On the other hand, you want to keep the main features of the natural images. So by keeping features, we use convolutions because convolutions can extract the local shifting variance features of natural images and the natural speeches. So that is the main idea. Of course, in the process, we reduce the dimension, but we use more and more channels to extract more and more features. So let me review the classical fully connected neural networks. So the input X is a vector in our D. D usually is very large, like 150,000. And then we take dot product with this input vector X by some vector to be trained Wj. Wj dot X plus Bi, that's one unit, and then activated by an activation function sigma. If you take altogether n such hidden neurons, then that's the linear combination of these hidden neurons. That's the output of the so-called shallow neural networks. So if we express this in terms of a matrix T1, which is formed by the rows as the trainable vectors, then the matrix T1 is n by d. So altogether, there would be nd parameters to be trained, which is a lot of d is large and n is even larger. So of course, we can use multi-layers to define iteration relation by the equation 1, which is activated by an activation function sigma component-wise. And at each layer, we have a matrix TL to be trained and a bias vector BL accordingly. So the last layer is TJ, T capital J. We take linear combinations. That will be an output function FTBC. So TBC are all parameters to be trained. Okay, so the key challenge in deep learning often is the dimension of this space is extremely large. The number of parameters we need to train is extremely large. So that's why the idea is to reduce the number of parameters by imposing structures of the neural networks so that the number of parameters can be reduced, but most of the structures can be kept. And with this, then we learn the prediction function by minimizing the least square or logistic or cross entropy loss functions. This is the learning algorithm. So a lot of research has been done along this direction, say to show the global or local convergence of this stochastic gradient descent algorithm in training the parameters. What I want to talk about is approximation theory. Since we know that if the hypothesis space is given, then the structure is clear, and we want to know how powerful the hypothesis space is doing in modeling the prediction functions. So once the approximation theory is established, then you can simply estimate the sample error and then get the generalization analysis of the learning algorithm. So the classical theory for is for fully connected neural networks. Even for the shallow neural network with even one hidden layer, we know that as long as the activation function sigma is not a polynomial, then for any compact domain omega bar d and any continuous function f1 omega, as long as the number of hidden neurons is large enough, we can approximate this continuous function to an arbitrary accuracy as you want. So this theory was developed about 35 years ago by a lot of people in approximation theory, neural networks, and so on. So typical result is this given by Mashka, saying that if the function you want to approximate has, say, rth derivative, then the rates of approximation can be n to the minus r over d, where d is the dimension. If the dimension is large, then this rate will be small, and n is the number of hidden neurons. But anyway, this shows us that as long as n is large enough, then we can approximate the function f well, although the dimension d will give us trouble if it's large. Now, in recent developments in deep learning, we often use rectified linear unit or its variance, which is defined by the maximum of u and 0. So it's piecewise linear. And what's nice about this is it can overcome the difficulty of gradient vanishing problem in parameter training, because the derivative of sigma is either 0 or 1. So the gradient would not vanish if you iterate many, many times. But the difficulty is this activation function does not satisfy the classical theory, because the classical theory requires that the activation function does not vanish. Its derivative, each of its derivative does not vanish at one point b. So we require usually that the activation function is C infinity, and it does not vanish at a point. All its derivatives does not vanish. So so it's different. The ReLU is different from the classical sigmoid type activation function, but still it has very nice approximation properties. So Tegowski and Yarowski showed that if you take more and more layers, then you can approximate functions better and better to get universality. However, our recent finding shows that actually you do not need many, many layers. Even the shallow nets are good enough in approximating functions. So the first work along this direction is Krasovsky and Baron, showing that if the approximated function belongs to the so-called baryon space, having satisfying this Fourier decay condition, then the rate of approximation is n to the minus half. And then Ziegler and Zhou, they showed that if the function f can be represented by neural networks of infinite widths, then we can get rates of convergence. So our recent work, this is first work with my former student Mao, and then another work with my former postdoc Yunfei Yang. We show that for really shallow neural networks, if the approximated function f belongs to the Holder space with smoothness index r is greater than 0, then if r is between 0 and d plus 3 over 2, then the rates of approximation is the same as that of the classical theory, which is n to the minus d r over d. If r is greater than d plus 3 over 2, then it's n to the minus d plus 3 over 2d. With these rates of approximation, then we can derive minimax, almost minimax rates of convergence for regression, which has the rates of m to the minus 2r over 2r plus d log m. So up to the logarithmic term, this is minimax rates of convergence in regression. And if r is greater than d plus 3 over 2, then it's m to the minus d plus 3 over 2d plus 3 with a logarithmic term. So this shows that even though we only use one hidden neuron, one layer of hidden neuron, still the approximation power is pretty good. So it means that if you only want to extract the smoothness of the target function, actually you don't need many layers. One layer is good enough. But in practice, we know that deeper neural networks are better than shallow ones. So we want to know which kind of structures of the target functions play a role in the power of deeper neural networks. And that's what we want to study. So we want to know not only the smoothness, but some other structures are playing a role in the good performance of deeper neural networks. So I want to describe one for deep convolutional neural networks. So let me start with convolution. We all know that convolution usually is defined, here we consider only 1D, so it's defined for sequences on the set of integers z. So if you have two sequences, w and x, the convolution, w convoluted with x is another sequence which is defined by the summation of wi minus k xk for k runs over the set of integers. And if w is supported on the set 0, 1 over s, say s is 2, then only 0, 1, 2, 3 unknown, possibly non-zero entrants of the sequence w. And if x is supported on the interval 1, 2 until d, then the convoluted sequence is supported on 1, 2 until d plus s, and it's given by this expression. So this expression actually gives us a connection matrix in deep CNNs. You notice that it's wi minus k, and so we know that the possibly non-zero entrance of this convoluted sequence is supported on the set 1, 2 until d plus s. So if we take all these possibly non-zero entrants as the output, and the input x is xk, k from 1 to d, output is I from 1 to d plus s, then the connection matrix TW is a topless matrix, which is given by this nice structure. So we can see that on this line, all the entrants are W0, and then the second line, all the entrants are W1, W2 until WS. So although the size of this matrix is D plus S by D with many, many entrants, but the trainable parameters, the number is only S plus 1. If S is 2, then there are only 3 parameters to be trained. So that means we only need to learn 3 parameters in such a connection matrix instead of D plus S times D entrance. So because of this reduction, we know that this matrix TW, the convolutional matrix, is very sparse. And here is the definition of the deep CNNs. When I wrote a review article for EEE, I found that actually in 1989 and 1990, people have already introduced these types of CNNs many, many years ago. So suppose we consider altogether J layers, small j from 1 to capital J, then the iteration relation is the same as before for the fully connected neural networks, except that the connection matrix Tj now is a convolutional matrix. It's a topless matrix with only S plus 1 possibly non-zero entrance. Okay, so because of this, the structure is the same, but the number of parameters we need to train is much smaller than before. And so then the hypothesis space for learning is you put all possible output functions together by taking the linear combinations of the last layer Hj. And of course, the filters W and the bias vectors are flexible. So the problem with deep learning training is the hypothesis space is the union of many, many reproducing kernel Hilbert spaces instead of one. So this actually leads to the problem of so-called lack of robustness, because the hypothesis space is the union of many, many spaces, not the summation. So the structure is not so stable. If you change the parameter a little bit, the function space changes. So therefore, the stability or robustness of the algorithms becomes a problem. But the advantage is that the number of free parameters to be trained is much smaller by imposing the convolutional structures for the connection matrices. In fact, the number of parameters is only 3sj minus 1 plus 2d plus 2j. So just imagine if the input data dimension d is about 150,000, s is only 2, then j can be also hundred thousands, which means that we can use many, many layers in our algorithm because the number of trainable parameters is still of the same order. So the first theory along this direction is the universality, saying that if the filter size is between 2 and d, which is fixed, typically we take S to be 2, like in the AlexNet, S is starting from 10, then 5, and then 2, and then some other convolutional neural networks. Typically, the filter size is only 3 by 3, meaning that S equals to 2. So the theory says that if S is fixed, then for any compact subset omega bar D and any continuous function f on omega, then there exist sequences of filters W and bias vectors B such that the uniform distance from the target function f to one of the output function can be arbitrarily small. That's the so-called universality of approximation. And the idea has been, that's my paper in 2020. And the idea has been deepened to a joint work with my former postdoc to almost sure convergence. Rates of approximation. So suppose we assume that the target function has R smoothness in L2 Hardy space, HR is embedded in C if R is greater than half D. So therefore, we assume that R is greater than half D. Actually, we assume that R is greater than half D plus 2. Then with this assumption, the rates of approximation is, roughly speaking, is capital O of 1 over square root of J, where J is the depth of the deep CNN. So if you take more and more layers, you can actually approximate beta and beta. So what's special here for the 1D CNN is we use zero padding. Zero padding means that this matrix, so if you look at the middle entrance, it's just this vector dot product with part of the input sequence, which is nice. But at the beginning or at the end, near the boundary, we take only one W0 dot with X1 because we assume that the entrance outside here or after here are 0. This is so-called zero padding, meaning that if the entrance are not available, we put them as 0. This is reasonable for speech recognition for 1D signals because we, when we say want to process a sentence, you start with some moment and end with another moment. So before that or after that, the sentence actually is considered to be 0. But for image, it's different because for image, when you take a picture, the things outside are not 0. So therefore, for 2D CNNs, we cannot use zero padding. That's the essential difference between 1D CNN and a 2D CNN. So that's why for 2D CNNs, usually we use a lot of channels to fulfill the gap. So then, as I said, if we use only a smoothness of the function, actually shallow ReLU networks are good enough. But deep CNNs are very powerful in practice. So we want to explain why. The second part of the theory is to show why CNNs are better than fully connected neural networks. So we start with the first theorem saying that deep CNNs are not worse than the fully connected neural networks. So we use downsampling operator, saying that if a vector is in RD, we only take one entrant out of every M, then the size of the vector is reduced by M, and we take this downsampling at some layers. So the theorem says that if you give me a fully connected neural networks, capital H, may have L layers, then we can always find a deep CNN with downsampling operations such that the output functions, the last layer will be the same. Okay, so the last layer of the deep CNN and the last layer of the fully connected neural networks are the same. Therefore, their hypothesis spaces are the same, but the number of parameters of the deep CNNs is at most 8 times of that of the fully connected networks. So it shows that deep CNNs are at least as good as the fully connected networks. But then we want to know why it's better, not only not worse. So we consider that the target function must have some structures, therefore the deep CNNs perform better. So the first family of functions we consider is rich functions, which takes the form of g c dot x. The input variable x is a vector in RD, and essentially it's a univalued function induced by a univalued function g, but it's induced by a dot product c dot x, where the vector c is unknown. So this is a rich function, and we show that if the target function is a rich, then we can approximate this function in on RD at the rate of n to the minus alpha if the univalued function is Lipschitz alpha. It shows that this rich structure actually enables the deep CNNs to get very good rates of approximation, although the algorithm itself does not know the rich structure, but the convolution automatically extract the convolution, the rich structure of the target function. The second family we consider is radial functions. So the function takes the form of fx to the norm square. So although it's a function of the variable x in Rd, but because it's only induced by a unit variable function f acting on the norm square of the input variable x, so it's a radial function. Now, if we consider the function to be of radial, then actually deep CNNs are better. So we compare with the shallow neural networks. If sigma k are all the same, then this is the shallow neural network. But here we even allow this to be flexible, meaning that the hypothesis space is even larger. Even with this larger one, the rates of approximation is actually very limited. Says that the rates of approximation is at most n to the -1 over d -1. So if the dimension d is large, actually this rate is very slow. And this is approximation by shallow neural networks. However, if we use deep CNNs, then the rate can be n to the -12. So which means that the rate actually does not depend on the input dimension d. This should tell us that if the function has the radial structure, actually the deep CNNs can automatically extract the radial structure, although the algorithm does not know it, but it automatically extracts the structure, and therefore we can get very good rates of approximation. So a generalization is the same. We consider this regression algorithm, and the target is to learn this regression function, which is the conditional mean. And then it tells us that the rates of approximation or convergence for regression is m to the -α over 1 plus alpha. Here, the target function, the regression function is a radial function. So essentially, it's a univariable function. Therefore, the rates does not depend on the dimension d here. So again, it tells us that if the target function have some structures, radial ones, then the deep CNNs learn better. Actually, we can consider many other functions with structures. We call functions with multi-features. So essentially, there are D star features, F1, F2 until F D star, and then induced by another function G of variable D star. This includes the model of hierarchical interaction models, radial functions, and functions with multiple polynomial features, and so on. So for such functions, deep CNNs actually perform very well. So recently, we have done some other results along this direction by deep CNN in approximation. Like we can show that deep CNNs perform well in classification, and they can also do well even if the loss function is logistic loss. And we consider also learning operators on infinite dimensional spaces. And recently, we are studying possible theory for transformers, but it's extremely difficult. So I hope I can report this later on. But that's what I want to talk about here today. Thank you very much for your attention. Yeah. Yeah, this is a very good question. No, it's not. Our generalization bounds actually is not like this one, for example. It's only m to the -α over 1 plus alpha. The minimax one should be 2 alpha over 1 plus alpha. But we haven't achieved this. And the main reason, because the function is essentially one dimension. The main reason is for the sample error part. Actually, we have not get the sharp estimates. So this is a very good question to work on, actually.
Any other questions?
Yeah, hi. Thanks for the nice talk. I didn't catch the part where you said this is a 1D CNN and that's why we just need one channel. Because I think the analysis or the derivation was just based on having one channel at each of the layers. So my question is, what would change if we had more channels? And what is the difference of that with respect to 1D, CNN, 2D, and so on?
Yeah, thank you very much. Yeah, it's a very important question. The reason is for 1D, as I said, the speech starts somewhere and then ends somewhere. So therefore, before that, and that, after that, the input data you consider to be 0. And therefore, in 1D convolutions, if you look at the matrix here, the first row has only W0 because you assume that starting from X0, X minus 1, and so on, all these are 0 entrants. So therefore, the dot product is the dot product of Ws until W0 with X minus S until X1. Okay, but all these are 0, therefore, we can use this in the 1D CN. But for 2D, it's not, because if you take an image, this is only part of the thing, and you know that outside of the image, the pixels are not 0, so you cannot put 0 as the entrant of the missing 2D function. So for that, then since you cannot use the 0 padding, so you have to reduce the range for the convolution. You can only do the convolution inside of the image. So with a small matrix, you take dot product with parts of the image, but you can only take the inner product inside of the image. So that's why the size of the image will be smaller and smaller. So you have to use many, many channels to extract enough features. But for 1D CNN, as I said, you can assume that the signal is 0 before 0 and after D. So therefore, one channel is good enough. Of course, if you use more and more channels, the approximation can be better for sure. And you can even prove theoretically that if you use more and more channels, the number of layers can be reduced. Yeah, that's a very important question, actually. The difference between 1D and 2D.
Any other questions? No? So then I think it's a good time to finish. So thank you very much.
So my talk is about learning under distribution shifts. So the goal is quite simple. So we are given label training data. So here X is an input variable and Y is an output variable. And we are given paired samples, label data from PTR, so training distribution. Then our goal is to learn a predictor Y equals f of X that minimizes the test risk. So test risk means we consider a standard loss function here, and loss function is expected over some unknown test distribution. And in practice, we may have some additional data to the training data, but I will talk about it later. And then we want to minimize this test risk with respect to a classifier or predictor F. Then the challenge here, technical challenge here, is to overcome changing distributions, because often the training and test distributions are not the same in practice. For example, some non-stationarity of the environment. So if we analyze brain signals, for example, then our brain is quite non-stationary and the situation is not the same over time. Or nowadays, even more seriously, so due to privacy concerns, we are not allowed to collect training data as we wish. Then our training data is essentially biased compared to the test distribution. So that's the target here. And this topic is actually not really new. And so in 2006, we organized a workshop at New RIPS, at the moment NIPS. And at that moment, there was no name for this problem. So we had a workshop named NIPS Workshop on Learning When Test and Training Inputs Have Different Distributions. It was one of the longest titles of the workshop so far. But so the workshop was a really successful one. We had a lot of great speakers there. And even those papers are quite cited nowadays. And after 3 years of the workshop, we finally published the book from the MIT press. This is basically an edited volume from the workshop. And there, so we named this problem dataset shift. But nowadays, this problem is called distribution shift, renamed. And in the last 3 years, so there are other series of workshops on distribution shift at New Reefs. So this topic seems to be back again and becoming more important nowadays. Yeah, that is distribution shift workshops. Okay, so my talk has 3 contents, and first one is to review some basic technologies based on importance weighting. So we have actually several different types of distribution shifts, and the most general one is joint shift. So joint distribution, P of X and Y, so changes between testing and training and testing. So this is the most general phenomenon, and we want to analyze this situation in the end. But this is the most challenging problem. But often we consider more specific problems. For example, covariate shift. So covariate is the name of the input variable in statistics. So covariate shift means basically P of X changes between training and testing. So it's one of the kind of nice simplification of the problem. Then another popular situation is called label shift or class prior shift. So P of Y changes between training and testing. Basically, class proportion changes between training and testing. Then actually output noise can also be formalized as distribution shift because P of Y given X actually changes. So in the training phase, we are given noisy output, noisy labels. Then, so in the test phase, we suppose we have clean labels and we want to predict them. Then this can be actually formalized as a distribution shift problem. Then mathematically, we can also consider class conditional shift. So P of X given Y changes. I'm not quite sure how this situation can be used, but we can find several papers even on this class conditional shift. We can consider many different variations of distribution shift problems. Then for now, so let me focus on the simplest problem called covariate shift. And this was actually first proposed by Shimodaira. So he's a professor at Kyoto University already more than 20 years ago. So training and test input distributions are different. So P of X changes. But the output given input distribution, so P of Y given X, does not change between training and testing. So this problem, covariate shift, can be nicely illustrated in regression. So if we consider input densities, suppose we have this blue Gaussian, so P train. Then so we consider this black Gaussian, so this is P test. Then output given input distribution does not change. So we have the same regression function between training and testing. But we have different region of points. For training, we have data from the left-hand side. But for testing, we have points from the right-hand side. So basically from blue points, we want to make prediction of these black crosses. It's a kind of extrapolation problem. So that's a typical covariate shift problem. And we assume that we are given label training data. So we are given blue points as usual. And in addition, so we suppose we have unlabeled test data. So we don't know test data themselves, but we assume we know their input locations, based on which we want to adapt our predictor to the test domain. Okay, then, so suppose we just naively perform linear least squares on these blue points. Then we end up in having this kind of green line. So we fit blue points quite well, but it doesn't predict these black crosses well. And statistically, we can easily show that ordinary least squares, ordinary training is not statistically consistent. So it doesn't work well, even if we have infinitely many training points. But once we have importance weight, so importance is defined as PTE over PTR, and this weight is applied to this loss function. Then, interestingly, only from blue points, blue training points, we can obtain green line like this. Then, so we can somehow make prediction of these black crosses quite well. So these are weights, so positive values, no negative values. And in this example, actually, for most of the blue points, importance weights are almost zero, because points on the left-hand side are almost useless, and they have almost zero weight. And only like 5 to 10 points on the right-hand side, they have some reasonable positive values. And prediction is basically based on done based on these blue points close to the black region. So this is how importance weight works. It's a kind of soft weighting to select important training point. Okay, once we have importance weight, then so we can actually train a classifier to train a predictor in a consistent way. So if we have infinitely many points, we can obtain the optimal solution. But in practice, we don't know the importance weight. So how do we estimate the importance weight? So this is the first question, first classical question in this field. Then that's a problem called direct importance estimation. So the problem is, so we are given training and test input points. So we have X points from the training distribution and X points from the test distribution. And we want to estimate the density ratio, PTE over PTR. So this is the importance weight. Then one of the classical approaches is called kernel mean matching. So this is a very nice method, simple and nice method. So it tries to match the means of PTE and R PTR. So R is an estimate of this importance weight. Once we really have PTE over PTR, then PTR cancels and we have PTE. So by matching these two, we can recover the true importance weight. And this kernel mean matching method so tries to do this matching in a reproducing kernel Hilbert space in a very nice way. In this way, and everything can be computed from training data simply, and it has really a nice theoretical properties. And another method we worked on more than 15 years ago is called least squares importance fitting. So this is also a simple method. So we try to fit an importance model R to the true ratio by least squares. So R minus PT over PTR squared. So this is minimized. So at a glance, so the equation is a bit complicated, but once we expand this squared term, then we end up in having a simple expression like this. And again, everything can be computed from approximated by training data. So training and test input points easily. And this method can also be extended to Bregman divergence. So squared loss is a kind of special case of Bregman divergence. It can be naturally extended to other class of Bregman divergences easily. Then, so based on direct importance weighting method, so classically we approach the covariates problem in two steps. In the first step, so we first estimate the importance weight. So for example, by least squares importance fitting, and we obtain R hat. So it's an importance weight estimator. Then we plug this estimated importance weight in the weighted criterion and obtain the predictor. So it's a two-step approach, quite straightforward. And more than 10 years ago, this was the state-of-the-art approach. And also, actually, I had a lot of industry partners who really used this kind of approach. At the moment, actually, the method worked quite well. It did go well, but there's a clear limitation of this two-step nature. So we have some estimation error in the first step. So R hat, hopefully R hat is a good estimator of the true importance weight, but it may contain some small error. And this small error can be magnified in the second step. But the first step is done without taking care of the second step. So ideally, we wanted to perform the two steps in one step. But this was not so straightforward, and we didn't have any answer in 10 years or so. But a couple of years ago, we had a nice method. So that's actually, again, quite simple. So instead of estimating the importance weight directly, we first try to have an upper bound of the test risk. So this is a test risk squared divided by 2. But this is upper bounded by some J function. And this J functional is actually a sum of these two terms. So J1 plus J2. Then we propose to minimize this upper bound with respect to both the importance weight and the predictor F. So by that, we can somehow solve the two steps in a single shot. So this joint upper bound minimization method can also have like theoretical convergence guarantee, and it is actually working quite well. But this method basically shows that so the previous two-step approach is suboptimal. Because now, so we can minimize, we can upper bound the test risk by the sum of J1 and J2. And classically, we minimize J1 first. Then after that, we minimize J2. But now we can directly minimize J1 plus J2. That achieves the lower upper bound. And this actually works also well in practice. Okay, that was a review of classical importance weighting technology. And still, I hope these technologies are quite useful in some applications. Then our current challenges are continuous shifts. So far, we focused on a fixed test domain. So we had training domain and test domain, and we tried to adapt our training predictor to the test domain. But maybe test domains can also change over time, like this. Test time 1, we have some test distribution, and test time 2, we have another distribution like this. And it continues until test time t. So roughly, so we want to obtain a predictor ft hat that works well for each pt over t equals 1 to t. So this is not a precise definition, but roughly we want to update our predictor over time to kind of follow the changing distributions over time. Then for now, let's focus on another simple setting called label shift. So only p of y changes over time. So, but p of x given y does not change. So it's another simplification of the problem. So only class proportions changes over time, like this. Then the setting is quite the same. So we are given label training data in the training phase. Then at each test step, so we have a small number of unlabeled data like this. So not only 1 point, but we assume we have small set of unlabeled test data. So that is actually needed to adapt our classifier over time. So this is our method called Atlas, adapting to label shift. So naively, we can perform batch importance weighting over time. So label shift can also be handled similar to the covariate shift case. And it's even simpler. So we can apply batch importance weighting, but this is computationally inefficient. So we want to do this updating process in an online way. So we use online learning, and more specifically, we use the simplest one, online convex optimization. So by assuming, so we use a convex loss function like a logistic loss. And also we assume that we use a linear model, f of x is just given by W transpose x. And in practice, we want to use like neural networks. So maybe in the training phase, we train a deep neural network and just fix all the feature extractors. Then only the final layer is trained, adapted over time. Then so we can handle it basically as a linear model. Maybe this is a kind of practical implementation of our method for neural networks. But theoretically, we focus on the linear model setting. Then, okay, here is just a simple gradient descent. So wt minus 1 is a current parameter, and we just compute the gradient of the empirical risk, and then so take the gradient step like this. And we also need to project the parameter onto the feasible region and obtain the next parameter. So this is the standard implementation, and it should work well. But the technical question here is actually the step size eta. So if the speed of distribution shift is quite slow, so almost unchanged, then so we suppose our previous predictor is good enough. Then we don't have to really change the solution rapidly. So in that case, so eta should be small to keep the previous solution. We don't have to change the solution a lot. But if the distribution changes more rapidly, then eta should be large so that we can quickly update our classifier to the new distribution. So if we know the change of distributions exactly, then actually we can choose the optimal eta in some way. But in practice, we don't know the distribution shift. So how do we choose eta in practice? So that's the question here. Then our proposal is to use an ensemble learning. So idea is again quite simple. So we prepare different learners with different speed. So we prepare M learners and having different learning speed, step sizes like this. And each of them is updated over time. Then the final output is basically the weighted average of these M learners in standard ensemble learning way. And the weighting is done by a classical method called H algorithm. We just take a standard exponential weighting like this. Then so the question is whether this is a reasonable idea. And we actually have a very strong theoretical guarantee for this atlas algorithm. So first we defined shift intensity Vt like this. So this is basically the difference between Pt of y minus and Pt minus 1 of y. And so for all classes and for all time. And if this shift intensity is small, then actually the analysis is quite straightforward. So I just omit that case and I focus on the situation where Vt is relatively large. Then we need to really take care of the distribution shift. Then suppose we know this shift intensity Vt exactly. Then so actually optimal step size is given by this quantity. Then actually this dynamic regret achieves this value. So here, so RT-WT is the risk of our model at time t, and RT-W mean is basically the best model at each iteration. Then this difference is summed over all t, and it's expected. So this is dynamic regret, and this value is achieved for the optimal step. So by the way, so if we consider standard regret analysis, then mean is usually outside sigma. Then basically we choose like the optimal parameter averaged over all time steps. That's a standard definition. But here, so our competitor is much better. So at each time step, the mean is taken. So this is much stronger, but we try to like follow this optimal one. And our theoretical results shows that even when Vt is unknown, our atlas still achieves the same dynamic regret as this value. So we don't know Vt, and we only prepare M learners and having different step sizes and take them ensemble. But still the same kind of dynamic regret is achieved. So in practice, we need to choose the number of learners, set the number of learners to this number, so log t. So if t is large, maybe M is also large, but still it's a logarithmic order. Maybe this is still acceptable. Then the step size is equidistant in the logarithmic scale. It's also a kind of standard choice. Then by that, we can achieve essentially the same dynamic regret as the known case. So that's a very strong theoretical guarantee. So then, so last NeurIPS, we extended the previous result to covariate shift. So it's continuous covariate shift adaptation. The setting is quite similar. So input density PT of X changes over time, but P of Y given X does not change. And again, we are given a large number of label training data in the beginning. Then at each time step T, we are given a small set of unlabeled data like this. And today, I don't really go into the detail because the method is unfortunately a bit technically complicated, but we can actually upper bound the dynamic regret of the predictor by like dynamic regret of an density ratio estimation error. So then we perform online density ratio estimation to update our density ratio predictor. Then at the same time, we can minimize the dynamic regret of the predictor. So in the end, the theoretical analysis is quite similar, and also algorithm is rather similar, but the mathematics behind was actually quite different. So that's why I couldn't really go into the detail today. But it's quite interesting that like two similar problems have like two similar solutions, but math behind are actually quite different. Then finally, I want to talk more about our ongoing challenges. So we have been interested in the distribution shift research for many years, but many distribution shift works so far basically consider a specific type of distribution shift. Like in our case, covariate shift, label shift, like P of X changes, but P of Y given X does not change, or something like that. But in practice, identifying the shift type is the most difficult part. And in particular, our case, we don't really have label data from the test domain. Then basically, so we are just given unlabeled data from test domain. Then there's no way to confirm whether the current shift is covariate shift or whatever shift. So it's just an assumption and belief. So then, so to overcome this situation, so let's consider joint shift. So P of X and Y changes. basically this contains everything. And once we have a reasonable algorithm for this setting, then so all the headache is gone. And 4 years ago, so we had a simple method called mini batch wise loss matching. So in this paper, we assume that, so we have a large number of label training data as usual. And also we assume that we have a small number of label test data. So now we need a label from the test domain. Then, so we use neural network and we perform mini batch wise training. Then for each mini batch, so we perform importance weighting estimation. And this is importance weighted criterion. And here we use so kernel mean matching, also a bit in a special way. Because now, so in mini batch training, we have a reasonable number of label training data, but very small number of label test data. So then, so direct importance weighting may not be so useful in practice. But once we perform kernel mean matching for loss values, so we have loss function here, it's a scalar value, and multiplied with some importance weight Ri. So this should be an approximation of this one. The left-hand side is the training error, and right-hand side is computed from a very small number of label test data. And we try to match them and obtain Ri. So this is possible by kernel mean matching based on loss values. Maybe the obtained solution is really poor because we only have a small number of label test data. But this is just one step of stochastic gradient descent. So as long as we can find a reasonable value for gradient descent, one step of gradient descent, then it should work well. And in practice, this method seems to be reasonably working well. So I don't think this Ri obtained in this procedure is good enough, but this is actually enough to adapt our classifier to the test domain. Then, so last year, we tried to extend this method to out of domain problem. So because the clear limitation of importance weighting approach is that the training domain must cover the test domain. Because we use this quantity, PTE over PTR, the PTR shouldn't be 0. So this basically means PTR should cover the entire domain, and PTE should be included in the training domain. So this is actually somewhat different from our intuition that in the first example of covariate shift, we wanted to do a kind of extrapolation. Like we had training data from the left-hand side and test data from the right-hand side. We wanted to make extrapolation. But this was not really true in that case, because we assumed we have Gaussian distribution for the training distribution. Then basically the Gaussian tail still covered the test domain. That was the kind of hidden assumption behind. But in reality, we really want to solve a problem like this. The test distribution is sticked out from the training domain. And we want to somehow identify this point. Then, so our method is still heuristic, but we had one nice method to do that. So we try to identify this point by applying outlier detection method. In our case, we used one class SVM to split the test points into the training side and test side. And those test points in the training side, so we apply importance weighting as usual. Then test point in the test region, pure test point. We directly compute the loss values over test point. But by the way, this is still a joint distribution shift, and we assume that we have a small number of test data. So that's why we can utilize pure test points as test point and just sum them up. So then, okay, this actually works quite well in practice. So I think this is the kind of first method we can really handle out of domain extension in this context. So then our ongoing challenges are here. So for joint shift adaptation, we require a small number of label test data. But in practice, this is very strong. Maybe we don't really have label data from the test domain. Then, so our idea is, so whether we can utilize weakly supervised learning in this context. And weakly supervised learning is another line of research our team conducted for about 10 years now. And so I don't really go into the detail, but we have an kind of unbiased risk estimation approach for weak supervision. We consider 7 different weakly supervised learning problems, and then for each of them, we can obtain an unbiased risk estimator. And this is basically based on empirical risk minimization. So we can use any loss function, classifier, optimizer in this framework. It's a fairly general approach. And we had a book on this machine learning from weak supervision 2 years ago. I hope that you have a chance to look at it. So let me just briefly explain one problem called PU classification. It's one of the simplest problem of weakly supervised learning. So it's a binary classification problem, but we only have positive samples and unlabeled samples. And we're supposed to have red points, negative samples on the right-hand side, but they are completely missing. So we only have blue points and black points. But still, we want to separate blue points and red points. So that's PU classification. Then, so after a few lines of simple mathematics, we can show that unbiased risk estimator can be computed only from positive data and labeled data in this way. Then, so for some simple parametric setting, we can achieve the optimal convergence rate. This is based on the standard empirical risk minimization. It's a fairly simple approach. So like this is an example. So we can solve a classification problem only from weak supervision. And we hope that, so for joint shift adaptation, so we can do the same thing. We don't really have to require strong labels from the test domain, but some form of weak supervision hopefully should be sufficient to perform joint distribution shift adaptation. Then this would be, I think, very strong mathematical tool for machine learning people. Because in practice, so like when we project any machine learning project, so we don't have data. We only have a small number of label data, and we have like less knowledge of the domain. Then we just pick up some standard method like least squares or whatever, then see whether machine learning is really useful or not. So like that, we want to really have a very general approach that has some minimum guarantee. But least squares is again, so it requires there's no distribution shift. But in practice, our distributions are changed over time, and we don't really have strong labels, and a lot of constraints are behind. So we hope to have a kind of very general method that can be applied to a problem without almost no assumption, but hope that we can still provide like minimum theoretical guarantee. Maybe the solution is not strong enough, but still it doesn't perform too bad because we should have some theoretical guarantee. Then, okay, at least we can use that kind of general method to judge whether like it's worth spending more money on this project or not. Once we find that, okay, machine learning is somewhat useful in this project, then, okay, we try to collect more knowledge about the domain, or we spend more money to collect label data or something like that. So that should be the first method we should use in practice. And also, good news is that this PU classification was found to be quite useful in signal enhancement application. So this was actually selected for the best paper award at ICASP last year. It's the simplest problem. So we input noisy signals, and we want to have clean signal as an output. To train such a system, so practically, so people used so-called parallel training data. So they wanted to have a signal of like noisy version and clean version. Then so train a denoiser. But in practice, so it's impossible to obtain such parallel training data. So then, so people basically generated artificial noise. Then, so added artificial noise to the true clean signal. So by that, they simulated parallel training data, but this doesn't generalize so well. But once we apply this PU learning technology to this problem, then, okay, so the situation is a bit tricky, but we treat noise as positive class. Then we can easily collect noisy signals in some environment. So these are positive samples. And then we can also collect noisy speech in some noisy environment. And this is actually unlabeled data. It's a mixture of noise and signal. Then we can just naively apply PU. Then only from noise, pure noise and noisy signals, we can separate noise and signal. And in practice, we apply like a Fourier transform to transform the data into the time frequency domain and apply this technique. But just that, so we can apply PU classification to really extract signals without really knowing the pure signal. So that's a kind of advantage of using this kind of weak supervision, and hope that we can extend this kind of approach to continuous distribution shift, so that we can really solve a difficult problem without really having strong assumptions. Okay, that's all for today. Thank you very much.
Data, you have much longer strings, but the longer strings are generated, can be generated by subset of the shorter string. So I wonder if you have never considered this setting, but this is a very common setting where you have compositionality, so you can compose smaller strings in order to get longer strings.
Yeah, thank you very much. That sounds like a very nice problem setting. So far, we focused on the kind of simplest standard setting, and once we have some more domain knowledge, then we try to add on those knowledge to the standard techniques. And still, we are on the standard level. So if you have knowledge like that, I'm sure.
Yeah, I think there are many problems that us as humans are actually applying that. If you think about, for example, arithmetic expressions, so we learn how to solve small expressions, and then we apply a compositionality principle on longer sentences. And so in this way, we are able to do out of the distribution generalization.
Yeah, that sounds great.
So I think you should consider this kind of problem where you have a set of generators. You don't know the generating function, so then the task is try to discover what is the generator function, and in this way maybe you can do better.
Yeah, sounds great. Thank you very much.
Thank you.
All right, so thanks very much for the comprehensive talk. I have two questions. So the first one is in the second part when you talk about the continuous distribution shift. So it's under the label shift assumption, right? So, but in the setting, if I recall correctly, at each time step, we don't have labels from the target domain.
Right.
So how to estimate the importance ratio between the labels?
Yeah, so I didn't go into the detail here, but so there are already like a line of research estimating the importance weight or PT of Y only from unlabeled data and labeled training data. And we just use one of the methods like that.
Yeah, I see. So it's can be like an estimate under certain assumptions, I guess.
Right, we need some assumption to make those methods like work really well in practice.
Gotcha. Yeah. So my second question is like a more general, because there are two types of like works in this literature. One is say we make explicit assumption about the difference between two joint distribution, like covariance shift or label shift. The other one is let's be agnostic about what specific assumption we make, but instead say the joint distribution is within certain ball. When I say certain ball, I implicitly assume certain metric, like for example, KL divergence or what's the sign distance. And how do you compare these two type of approach? Because obviously the first type, this kind of assumption does not always hold in practice. For example, for image data, they can have like a non-overlap support. But for the second type of approach is very pessimistic in the sense that usually the worst case distributions may not be like the realistic ones we encounter in practice. So like how do you feel as a community we should move forward, and which kind of like assumption about the underlying data we make that can lead to, on one hand, useful algorithm in practice, but on the second hand, also amenable for theoretical analysis, and we can make non-trivial guarantee about generalization.
Yeah, thanks for the great comment. Actually, I had the kind of similar slide, but I didn't show that today. But right, so there are clearly two approaches. And in our case, we suppose like we can somehow estimate the test distribution. We have some knowledge on the test domain. Then we try to adapt our current predictor to the known test domain or estimated test domain. That's one approach we are taking in this talk. Then we had also another line of research like distributional robustness. As you said, we consider certain like worst case scenario, and we try to adapt our predictor to the worst case scenario. We had also a paper along that line, but as you said, so those methods are extremely pessimistic and it doesn't really work well in practice. Like in the case of reinforcement learning, robot doesn't move is the best solution because it's the safest choice. Klaus?
Okay, so very nice talk, and I learned something new. one of the things that I found quite very interesting also was denoising that you mentioned, and I just have a silly question. So the first, I mean, probably you assume something about the noise content, but if you don't, have you ever thought about just, so to say, doing source separation? Because in source separation, you would have one other signal mixed in, but that's a structured signal.
True.
So can you comment on this?
Yeah, so right, so in our case, we assume that in the time frequency domain, so signal and noise are kind of separated and not overlap too much. But by that, we can cancel noise. Right, if two are completely overlapped in the time frequency domain, we need another kind of assumption. Then ICA could be one of the possible approaches.
Yeah, because, I mean, if you think about a male voice and a female voice, they don't fully overlap. So maybe it's possible.
Right. So
Because it's the, one microphone source separation is a very difficult task. So maybe
true.
you should try.
Hope that we can use some kind of weak supervision there. Thank you very much for the great suggestions.
Okay, so it's a good time to finish. So thank you very much.
Thank you very much.
I am Taiji Suzuki. I'm in the University of Tokyo, and I'm also team leader of deep learning theory in the RIKEN. So yeah, nice to meet you. So today I'm going to talk about some non-convex optimization by a kind of mean-field gradient method, like mean-field Nanjipan or Wasserstein gradient flow, and its application to something like reinforcement learning and in-context learning. Okay, so this is what we want to do in this presentation. So basically, we want to minimize some objective function f, which could be convex or non-convex. And f is a functional on a probability measure space. Okay, so mu is a probability measure. So we want to optimize a probability measure by minimizing some objective function f. And maybe so in some situations, there could be some entropy regularization. So this entropy regularization works to make the objective function like strictly convex. Then we have a strong convergence. Okay, so but in some situations there could be no entropy. Okay. So this kind of problem appears to train the two-layer neural network in a mean-field regime. So that is given by like this. So here, f mu is a neural network, which is given by this integral representation. Here, sigma is a nonlinear activations, and R is a second layer parameter, and W is a first layer parameters. We take the expectation with respect to the parameter R and W. So here, mu is a distribution with a parameter of each neurons. So then by optimizing the distribution mu, so you can fit the two-layer neural network to data. So this kind of problem so can be deduced to this general optimization framework. Okay, so especially so we are interested in something like reinforcement learning with the actor critic method, and some feature learning, in context learning by transformers. But I will show some convergence analysis in these problems. Okay, so first I want to start from a convex problem. So I want to start from a kind of a brief introduction of the literatures. Then I want to go into the more difficult problem like reinforcement learning and in-context learning. So, okay, so as I said, we are interested in optimizing the neural network, which could be written by like this. So today, so basically we consider only the two-layer network. Okay, so this is a one neuron. So each neuron can be denoted by hx, where x denotes the couple of the parameters, and R and W, the first and the second layers parameters. And then so we have an M neurons and take their average. So this is our neural network model. So because this is an average, so this is called a mean field regime. So if this factor is like 1 over square root m, it is called a neural tangential kernel regime. But here we consider the mean field regime. Okay. So okay, so now we want to fit this model to the data. So we prepare some loss function Li, and then we want to minimize this loss function with respect to the parameters. But maybe so you can add some L2 regularization. However, the problem is that the model fx is nonlinear with respect to the parameter x. So therefore, even if the loss Li is convex, so the non-linearity of fx makes this problem a non-convex optimization problem. So basically, so in general, it is difficult to optimize this objective function. Okay, to overcome this problem, so we consider a kind of over-parameterizations. We consider very wide limit, the infinite limit of the width. Okay, we take the width m to the infinity. Then maybe this finite average could converge to this integral. So here again, the mu is a distribution of the parameters R and W. You can see that this integral representation is just an extension of the finite summations, because if mu is like a discrete distribution, then this integral representation includes this average, just finite average formulation as a special case. But a good point of this integral representation is that this is a linear with respect to the distribution mu. So this is a kind of infinite dimensional linear model. So in a probability measure space. Okay. So because this is linear, so then we expect that it could be easy to optimize. Okay. According to these extensions, the model, so loss function can be replaced like this. Fx is replaced by f mu. And then this regularization term could be replaced by the expectation of the parameter x squared. So maybe this is just an L2 regularization. So now, if the loss Li is convex, like a squared loss or logistic loss, so because f mu is linear with respect to mu, so this objective function is linear to the distribution mu. So we have convex with respect to the parameter distribution mu. So we have a convex objective function on a probability measure space. Okay, more generally, so we want to optimize this kind of objective function where f mu is a convex functional on a probability measure space. So basically, we want to minimize this one. So to do such an optimization problem, so there is a so-called mean field Langevin dynamics. So that is given by this stochastic differential equations. Okay, so you can see that here is the objective function f. But there is some Brownian motion term. So because of this Brownian motion terms, it doesn't stack into something like a plateaus. Okay. So but by adding this Brownian motion term, so there is some additional entropy term like this. So actually, so this mean field Langevin is kind of so okay. So the Fokker-Planck equation with this mean field Langevin is a Wasserstein granite flow to minimize this entropy regularized objective function. Okay, so yeah, so there is some additional entropy term, but yeah, this makes the objective function more strictly convex. Then we have a convex convergence guarantee. But anyway, if you run this mean field Langevin, then the distribution mu t, which is the distribution of xt at time t, the mu t will converge to the global optimal solution that minimizes this entropy regularized objective function. So that is what we want to do. Okay. So actually, so the Fokker-Planck equation with the mean field Langevin is given by like this. So then this term tries to minimize this convex objective, and this term tries to minimize this entropy regularization. And I should mention that so there is some new notation del f over del mu. This is so-called first order variation of the functional f. So this is a kind of a this is the kind of the functional derivative on the measure space, which is formally defined by like this. So this kind of a notation will appear in the later slide. Okay, so anyway, so what we are doing is like, so we take the derivative of the objective, and then we try to minimize this objective function by running this stochastic differential equation. Okay. So then we are interested in, does this dynamics converge or not? So actually, under some assumptions, we have the convergence. Okay. So unfortunately, due to the time limitation, I don't go much details. But if there's something like so-called proximal Gibbs measure satisfy the so-called log Sobolev inequality, so which is a very standard assumption, then we have an exponential convergence of the entropy regularized objective function. Okay. So even though there's although there's some entropy regularization, but anyways, we have an exponential convergence. So this is a very good for us because we have a global optimality guarantee of the mean field Langevin. So just running the mean field Langevin, then you can optimize the convex functional on a measure space. Some more details will be explained by Atsushi Nitanda in the third day of this workshop. So he initiated this line of the work. So yeah, for more details, please attend his talk in the last day. Okay, so now, so as I said, so we can optimize, we can fit a two-layer neural network to the data by the mean-field arrangement. So then maybe so you are interested in its generalization abilities. So like statistical properties. So now we consider very simple settings, that is so-called case-sparse parity problem. So let us consider input z, which is a d-dimensional vector, which has ±1 in each coordinate, just a random ±1, so even probabilities. And then you pick up the first k coordinate from these d-dimensional vectors. Then you take the product. So then this is the output, so label y. Label y is also ±1 because zj, so each coordinate is ±1. So if k equal 2, so this is just an XOR problem. So this is a kind of extension from XOR problem to a little bit more difficult problem. Okay? So yes, so this is just a binary classification task. So you can fit a neural network by using something like a logistic loss. So and then just running the mean-field arrangement so that you can fit a neural network. Okay. Then as a result, so we can show that the test error could be bounded by d over n, where n is the sample size and d is the dimension of the input. So we have a d over n of the test error bound. So the good point is that to obtain a very bit small test error, the sample size n could be like order d. Order d is sufficient to obtain the small test error. However, if you use the kernel method, so which cannot perform the feature learnings, you should pay d to the k, d to the power of k sample complexities. So if you compare the sample complexity between the kernel method and the neural network, you see the significant difference. Okay. So for the neural network, you only need a order d sample complexity, but for the kernel method, you should pay the t to the k, exponentially large sample complexity. So this is because of the feature learning ability of the neural network. So we are using we are considering the mean-field neural network, so then we can do this kind of thing. So now, so because of this, so we want to apply this kind of analysis to other situations, like reinforcement learning or in-context learning, feature learning with the transformers. But the problem is that then the object function is no longer very well, simply convex. Maybe object function becomes like a non-convex object function. Then its convergence guarantee is not so trivial. So first, I want to explain our recent result on reinforcement learning. Okay, here we consider actor critic settings. Okay, so here R is a reward and gamma is a discount factors. In an actor critic method, there is an actor and a critic. The actor has a policy pi a given S. This means that for each state S, the actor takes action A according to this policy, the distribution of the action A. We want to obtain the best policy pi that maximizes the expected reward. Expected reward is just a summation of the expected reward in the future, okay, with some the discount factor gamma. Okay. So the summation of the gamma to the t times the reward from t equals 0 to infinity. But just to maximize this expected reward directly is a little bit difficult. So we prepare the so-called Q functions. This could be estimated in the critic phase. The Q function is almost the same as the expected reward, but it is conditioned by the current state and action S and A, like this. So if you have a Q functions, so then expected reward can be obtained by the expectation of the Q function with respect to the state and actions. Okay, so like this. So in an actor critic method, we iteratively update the policy and the Q functions. We update the policy, so then the Q function is also updated, and if after the Q function updated and the actor updates the policies, then it will converge somewhere maybe. So hopefully optimal policies. So yeah. So in this analysis, we assume that we consider that this policy is characterized by two-layer neural network FRO, which is a mean-field neural network. Okay, but this is given by the exponential to minus FRO, where rho is the distribution of the parameters. So here, okay, so this is our policy, And for Q functions, we also use a neural network. Then we estimate the Q function by two-layer neural network, where the distribution of the parameter is denoted by small q. Okay, so anyway, so we fit this two-layer neural network to the Q function and the policy function. Okay, so as I said, so in a policy gradient descent, so we need to estimate a Q function first. So I want to explain how to estimate a Q function. Yeah, so here, so we employ the TD learning framework. Okay, so this is a definition of the Q function, which is given by like this. So the Q function must satisfy that the zero temporal difference errors, which means that the Q function should satisfy the like Bellman equations. So that means that Q must be same as the current reward plus the expected reward in the next step state and actions with some discount factor gamma. So, okay, so Q must be equivalent to R plus expectation with respect to the next step state and actions. We read this term as a T pi QQ, okay, T pi QQ. So this is just like a one-step Markov chain. So then we take we denote it by T pi QQ. Then so yeah, so the Q must be same as T pi QQ. So then what we should do is to minimize this temporal difference with respect to the distribution Q. I mean the distribution parameter Q. Okay. So then for that purpose, we take the gradient. I mean, so first order variation of this TD errors. So then you get this kind of a first order variation. But the problem, so here is one problem where here is an expectation with respect to the next time step state and action. And then here is also the next step state and actions. But these are kind of a independent independent realization of the next step state and action conditioned by the current state and actions. Okay, so they have the same current state and action, and then we should generate an independent sample of the next step. But it is very difficult because if the state is continuous, so in some episodes it is very difficult to have to go through the same state and actions. So the expectation with respect to these terms are a bit difficult here. So the people usually consider to neglect this term. So then we can calculate this expectation by using like a stochastic differential allocation or stochastic gradient descent or online learnings. So if we neglect this one, it is called semi-gradient. So if this is a kind of a linear model, so that you can use the semi-gradient and you can show the convergence and some assumptions. However, in our case, so in our case like distribution optimization settings, we are using the Masashi gradient tool to optimize the objective. So then we don't have a guarantee of the descent direction so obtained by this semi-gradient. So we need some another strategies. So for that purpose, we propose a so-called proximal TD learning method. This is a very simple marginalization minimization approach. So this is very easy to consider. Okay. So as I said, so just optimizing the temporal difference directly is really difficult. So we consider a kind of very easy upper bound over the objective functions. Okay. Now suppose that at the nth iteration of proximal TD, so we have a solution QL. So then we have a kind of a quadratic upper bound of the objective function at QL, so which is denoted by LL. Okay, the upper bound can be obtained like this. This is a very tight upper bound of the objective function. So we have an surrogate objective which upper bounds the objective. Then we minimize this upper bound at each iterations. And so that minimizer is denoted by QL plus 1. But you may add some regularization like this. So TD error, upper bound of TD error plus L2 regularization. Then we minimize this with respect to the distribution Q. So fortunately, this upper bound is just a quadratic function with respect to the distribution Q. So this is a convex function. So that you can apply the mean field range band to optimize this objective. So actually just running this mean field range band, then as the S goes to infinity, you can get the minimizer QL plus 1. But of course, in practice, you should stop at some point S, large S. So we should take into account such a finite time errors. So then anyway, so we get this convergence rate. Okay. So in our inner loop, so we run the mean field arrangement, then we update QL to QL plus 1. So then we iterate that many times. So we suppose that we stop this outer iteration at the TTD. And so the inner iteration, as for the inner iterations, for this mean field arrangement, we stop large S from time to 0 to large S. Then we stop that solution. Then we obtain the approximated next solution QL plus 1. So then we have this upper bound of the objective function. Okay. So the main term coming from the outer iteration is like 1 over T. The second term is the inexact solution of the inner iterations, which is given by like exponential 2 minus some constant lambda S, where alpha depends on the regularization parameter lambda. But anyway, so we have an exponential convergence in the inner loop. Okay. So therefore, if the regularization parameter lambda is sufficiently small and the number of iteration is sufficiently large, so you have a good approximation of the Q function. So, okay, now we have a Q functions, approximated Q function. So then based on this Q function, we want to update the policy pi, okay? So, so the policy is updated to maximize the expected reward, which can be written by like this. But now, so we replace the true Q function by an estimated Q function QK. Okay, so we use this estimated Q function instead of the true Q function. Then we update this policy with respect to the distribution role. Okay, so we update a neural network to characterize the policy distribution. Okay, so here again, we applied a one-step gradient descent in a mean field arrangement. So here we consider a kind of discrete time versions of the mean field arrangement, which is given by like this. Then you can update the policies. So then we iterate this. So we update, okay, so we update the policy by just one-step mean field arrangement gradient descent. And then after that, you update the Q function, and then you update the policy, and we iterate that. So then here is a convergence of the entire algorithms. Okay? But the problem is that, so in each iteration, we don't have an exact value of the Q function. So we have just an approximated value of the Q function. So we need to consider such errors. So by taking into account such an error, so we have this convergence, with respect to the policy gradient. Okay, so here epsilon lambda is induced by the errors of Q function estimations. The first term is coming from the outer iteration of the policy gradient. But anyway, so we have a good convergence. If you set lambda sufficiently small, then you can have a good approximate of the optimal policies. Okay. So, but in a previous work, so people are usually consider neural tangent kernel regime, but this is a kind of a very fast work that showed our convergence for the mean field settings. Okay, so I don't have so much time, so sorry. Yeah. So then, finally, so I want to briefly explain the in context, the feature learning and in context learning in the last few minutes. Okay. Sorry. So yeah, so what is the in-context learning? So in in-context learning, so we have a pre-training. So after that, there is we will see test task. Suppose that you have a T tasks, and in each task you have a function ft o. So this is a true function, true input-output relation in the T task. Okay, so at T task, so FTO is fixed, and for at each task, so in that task, you have n data point, then we have this training data. Then we observe this pre-training task, the large T times. And we have this pre-training data. So then we train a kind of distribution with the function ft. And then by using that, so you perform a kind of base estimation in the test settings. Okay, you have n queries in the test settings, and based on these queries, you n prompts, and based on this training data, so you want to estimate output y for the new queries on this new task. This is what we want to do. So here we consider a kind of this specific situation where the true function ft is written by the written by this linear model, where FO is the nonlinear features for input X. So this is a k-dimensional vectors, and VT is a task-specific vectors. VT is distributed from standard Gaussian distribution. So VT transpose FOX is the true function FT at the T's task. Okay. So FO is fixed or across across different tasks. So then, what we want to do is to estimate these nonlinear features in the pre-training phase, and then we want to estimate VT in the test phase. Okay. So to estimate these features, nonlinear features, we use the mean field neural network like this. Here, the H theta, so each neuron with the parameter theta has an output vectors with k-dimensional real values. Okay. So H theta, the output from each neuron is a k-dimensional vector. Okay, and so we take the expectation with respect to the parameter theta. So then this is a mean field neural network with a multiple output neural network. Okay, so then this is the model of the nonlinear features. By using this nonlinear features, we perform in-context learning. Okay, in a test phase, so we use a linear attention. Then so we estimate the VT, which is task-specific vectors. The VT could be estimated by using this model. So here, this is for new input X query. We calculate the nonlinear features. And so we have observed n data points. So for those n data points, we can calculate the key and values. And so the gamma is a trainable parameter. So by modifying gammas, we want to make this linear attention model as accurate as possible. Okay. So so this part should be close to VT for each task key. Then we want to predict the output Y for the X query. The mean squared error of this model can be written by like this. I skipped some details, but anyways, just calculating the expectation so that you can see that the expected in-context learning risk can be written by in this explicit form. So now the question is, we want to optimize this objective function with this to the matrix gamma and the distribution mu, so which could be nonlinear objective function, but can we show its convergence? That is the question. So yeah, there have been many work on the optimization of our ICL for linear model, but here, so we are considering this nonlinear model. So that is our difficulty. Okay. So and as for the optimization, so we consider two time scale settings where for each distribution mu, we optimize the gamma. So gamma is just a k times k dimensional matrix. It is easy to optimize. This is just a least squares problem. So it's easy to optimize. Then we have explicit form of optimizer gamma for each mu. So then if you minimize the gamma, so then with the fixed mu, then you have an explicit form of the objective function with respect to the distribution mu. So we try to optimize this one. Okay, so we try to optimize this one. So because the objective is convex with through gamma, so maybe its convergence is faster than the optimization of the mu. And so yeah, so we can consider this kind of thing. Okay, so then now we try to optimize this objective by Wasserstein gradient flow like this. Then, so this is our main theorem of this part. Okay, we can say that even though this objective, okay, so I go back here. Even though the objective is highly non-convex with respect to the distribution mu, because here is a mu, so this is our like a quadratic, more than the quadratic function with respect to the distribution mu. So this is a very highly convex, highly non-convex. But we can say that the objective is something like a strictly saddle. I mean, so there's no spurious local minimum solutions. And if there is a critical points, but there is some negative curvatures. So in more precisely, so for each point mu, this either of the condition 1 or 2 happens. The condition 1 is that you can find descent directions. So this is the condition 1. Otherwise, the solution is on a critical point. I mean, the saddle point. And then you can find negative curvatures like this. You can find a negative curvature. So okay, the solution can find the gradient, descent direction, or so even if you cannot find the descent direction, I mean the gradient is 0, you can find the negative curvatures. Then just a small perturbations, adding a small perturbation, then you can get out of the local optimal, the saddle point. Then you can escape from the local optimal solutions. Okay, so this is our main result. And actually, so under some assumptions, you can see that the Wasserstein gradient flow Wasserstein gradient flow decreases the objective function, and then it can converge to the global optimal solution, hopefully in a polynomial orders. Okay, so this is our numerical experiment. I skip this. So this is the conclusion. So I have considered a mean field arrangement in the first part, and then I applied it to actor critic problem. And then so we also considered in-context feature learning, and we have shown that in in-context feature learning, the loss landscape is strictly saddle. So yeah, and the solution is not captured by the saddle point, and it escapes from the saddle point, and it converges to the global optimal solution. So thank you very much.
Thank you for presentation. So does anybody have questions or comments?
Hi, thank you for the talk. I'm wondering if anyone considers changes in lambda. I'm thinking kind of from the physics standpoint of annealing, in which if you want to find the minimum of F mu, yeah, you can raise the temperature and decrease it. And maybe this is a little bit related to the idea of distributional shift as well. Yeah.
Yeah. So could you explain? So yeah, so decreasing lambda is something like an annealing. So yeah, of course, in the worst case, so if you choose a very small lambda, so then the computational complexity could be very large. So because if you anneal this, then so you can, it is very hard to get out of a local optimal. So because the noise is small, so so very with small probability you can get out of a local optimal. So then the planning of the annealing should be very careful. So yeah, so I believe that just considering the annealing, so then something like a diffusion model appears, and then you can get a good solutions. But so far we haven't shown such a result. But yeah, but I don't know some relation to the distribution shift, but I haven't considered so much about that. But yeah, so it's an interesting problem.
Because maybe that's kind of like a slow shift in the labels somehow. Yeah.
Yeah. Thank you. Yeah.
Hi. So for the proximal TD, you showed that there's this convex upper bound for the Q function learning.
Yes.
Do you have some intuition for what that optimal solution represents for, because it seems like there exists one for every Q function?
Okay. So sorry. So you mean this upper bound? So the explanation why this upper bound exists or not?
Or no. It just what does the solution for that upper bound represent? Because it seems like there's one for every possible Q function, for every intermediate Q.
Yeah. So okay. So maybe the objective is not completely convex, but just so you can have a kind of this the quadratic function. So this is a kind of a gradient descent. So okay, so we cannot compute exact gradient. So it's very difficult. But as a proxy, so we calculate a kind of upper bound, which is easy to calculate. So actually, so the next solution QL+1 is something like a gradient descent on our function space, like L2 space. But to deal with to perform the gradient descent in the L2 space in a function space is very difficult. But very similar thing is happening here. So this is like a proximal gradient descent in L2 space. So yeah, so that is our intuition.
But there is a convergence guarantee for this series of convex.
That's right. Okay. That's right. We have a convergence guarantee. So because we are performing a kind of a proximal gradient descent in a L2 space. Then we have convergence. So this is very similar to the finite dimensional situations. Very, very similar. Yeah. But the non-trivial point is in a loop. So in an inner loop, so we need to perform a kind of infinite dimensional optimizations that can be performed by mean field arrangement. So once we have such a guarantee, the outer loop is very similar to the finite dimensional optimizations.
Thank
Yeah.
you.
Thank you.
Okay, one more question. Thank you for a great talk. And so I'm interested in in context learning. And then so my question is is it possible to characterize the property of the limit of the training? So at the paper says that in the linear input learning case, so the gradient flow combines to the least square solution, which maps data to the solution. So is that kind of a similar representation in your study?
Okay, so okay, yeah. Yeah, yeah, of course. So in a linear case, we can have a kind of sort of base estimations, or in a pre-training task, so we have a kind of sort of gamma is a fine. So to optimize gamma is equivalent to find the optimal regularizations. So there's something that's similar is happening, but the problem is that not only the gamma, but also we need to estimate the HMU itself. So the feature itself it should be optimized. So that is the most difficult part. But yeah, so up to that rotations, so we have a consistency. So in this situations, in this settings, so as we are considering the n and t goes to infinity in the limit. So then we have a consistency such that so the optimizer with this is just rotations. This is almost the same as it's same as if no, the true features up to the rotations. No, not the rotation, but invertible function. So yeah, so yeah, of course, depends on the solution age. So the optimal gamma is also changed, but yeah, that's right. Yeah.
Thank you very much.
Okay, thank you very much. Let's thank the speaker again.
Thank you very much.